Welcome back. Today we're going to talk about sequences. So this is a note on sequences, and sequences have to do with finding terms in a pattern. So there's a couple different things you can do with this. The first thing you can do is you can have an established pattern, find a rule, and then find additional terms from that rule, or you can have the rule and find the individual terms. And so as we talk about these things, understand we're doing a couple of different types of problems, and they're going to lead us into deducing and talking about some pretty mathematical language as we do this. So kind of be on the lookout for a lot of variables, a lot of generalized mathematical language, and we're going to talk about that in the context of sequences. So here we go. First term. First problem is find the next three terms, then write a general rule. So this is probably the part you'd be most comfortable with. Like, okay, I see how it goes. Oh, it's these next three. But writing the general rule can be the tricky part. So here we go. What I like to do first is just kind of look and label like the number of terms. So term number 1, 2, 3, 4. And obviously we see 5, 10, 15, 20, and we can go 25, 30, 35. Our goal with the general rule to find the kth term is to say k sub n equals something, and this formula you want to put in n, which is the term number, and get out the answer. So I don't want to have to recount the whole series. Like if I said, what is the 1000th term of this sequence? I don't want to have to count and figure out what the first 999 are to be able to do that. So what does it mean? Well, when n is 1, my sequence is equal to 5. When n is 2, it's 10, 3 is 15. So obviously, it's 5 times n, where n is the term number. Let's look at the next one. Well, okay, so to recount that. So what's the thousandth term? It'd be 5,000 because it'd be 5 times n. All right, so that's the goal of making a general rule. So this is the general rule right here. All right, next one. 2, 4, 8, 16, 32. I label 2, 3, 4, 5. How do we get from term to term? So this one looks like 2 to the first. This one's 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So that's my sequence. What part of this matches up with my term number? So the first term is 2 to the first, second term is 2 to the second. So it would be 2 to the nth power. 1, 1/2, 1/3, 1/4, 2, 3, 4. I could rewrite this as 1 over 1, and this is my first term, second term, third term, fourth term, so it's 1 over n. How do I generalize these things? You've got to be able to make a connection, and this is not a mathematical thing, but it's a problem-solving thing. I try to make them all look the same, right? So I could write this as 5 times 1, 5 times 2, 5 times 3. Well, that makes it easy to see how does it step up. This one will be 2 to the first, 2 to the second, 2 to the third. This one will be 1 over 1, 1 over 2. Try to rewrite it in a way that makes them all look similar. That can help you solve the problem. Sequences in general. Sequences in general are an ordered progression of numbers. It's an ordered progression of numbers, and what that means is it's logical, okay? It doesn't jump around. It's like I can get from here to here and I can find a pattern. Now, it's not always easy, but I can find a pattern to get there. Finite sequences have limited terms. For example, 2, 4, 6, 8. That's a limited number of terms. If it was only that, it would be a finite sequence. An infinite sequence goes on forever. That would be like 2, 4, 6, 8. And then this means goes on forever. The dot, dot, dot. Okay? These finite sequences are going to have, infinite sequences are going to have a general rule. Over here, you're not going to have a general rule because you don't need to just find the nth term. You don't need to be able to find the 106th term or whatever. For an infinite sequence, you can find any of them. Okay, here's a pretty common layout for this. Find the first 6 terms and the 100th term of the sequence a sub k, in which a sub k is equal to k squared minus 1. Well, what does that mean? A sub k is a sub term. So a sub 1 is the first term. And I want to find the first 6 and the 100th term. And so it's k squared minus 1. So a sub 1 is equal to 1 squared minus 1, which is 0. A sub 2 is equal to 2 squared minus 1, which is 3. A sub 3 is 3 squared minus 1, which is 8. A sub 4 is 4 squared minus 1, which is 15. A sub 5 is 5 squared minus 1, which is 24. A sub 6 is 6 squared minus 1, which is 35. So, what is my answer? My answer is 0, 3, 8, 15, 24, 35. And I put it in set notation because it's a set of answers. I got to have all 6, okay? My 100th term would be a sub 100. So I'd have a sub 100 is 100 squared minus 1, which is going to be 1, and then it would be 100 times 100. So it's 1 with 4 zeros. 2, 3, 4. Boom. Minus 1 would be 9,999. Answer. Not 9.99, 9,999. Okay. Next one. And I can switch up the notation. So they can say u sub n. Well, that doesn't matter. U sub n just means this sequence defined by nth terms. And so I did this one in columns. I'll do this one across. U sub 1 is equal to 1 plus 1 over 1, which is 1. 2. You almost got me there. U sub 2 is equal to 2 plus 1 over 2, which is 3 halves. U sub 3 is equal to 3 plus 1, which is 4 over 3. U sub 4, 4 plus 1 over 4, which is 5/4. And now you can see a pattern. So I've got 3 over 2, 4 over 3, 5 over 4. A sub 5 would be 6 over 5. A sub 6, I'm saying A, it should be U. U sub 5, U sub 6 would be 7 over 6. Okay, and so that's the general rule. So how does this work? Well, it's, plus 1 over whatever your nth term is. So U sub 100 is equal to 101 over 100. All right? So let's look. A recursively defined sequence. Recursively defined means the next term, and put that in parentheses, is defined by the previous term. Okay, so the second term is defined in terms of the first term. The third term is defined in terms of the second term. And so you got to look backwards to be able to find the next term. So what would that look like? Well, so here we go. Same directions, find the first 6 terms and the 100th term of the sequence defined recursively by the conditions. So the first term is 3, so b sub 1 is equal to 3. B sub n is equal to b sub n minus 1. So this means this term is defined by the previous term plus 2. So b sub n minus 1 means the one before it. So b sub 3, so if b sub n is equal to b sub 1, then b sub n minus 1 is equal to b sub 0. Okay, it's the one before. So if I'm trying to figure out what the next term is, and it's the previous term plus 2, so this literally means the previous term plus 2. If b sub 1 is equal to 3, then b sub 2 is equal to 5. B sub 3 is equal to 7. B sub 4 is equal to 9. B sub 5 is equal to 11. B sub 6 is equal to 13. Okay, that's exactly how this works. And so, what does this look like when I'm figuring out the 100th term? Well, the 100th term would be b sub 99 plus 2. So how am I going to figure out what b sub 99 is? Well, if I've got a generalized term that's defined previously by the one before, this can present a little bit of an issue. And so if you think about it like this, if I've got the 100th term, it's 99 terms beyond the first. So think about it like this. B sub 100 equals 99 times 2, because there's 99 terms plus b sub 1, right? So the first term, and then 99 sets of 2 is going to give me my 100th term. So I've got 99 times 2 is 198, plus 3 is equal to 201. Okay, so it works because every time you're adding the same amount, right? So like b sub 3, it would be 2 sets of 2. So b sub 3 was equal to 2 sets of 2 because it's 2 beyond the first term plus 3. Okay. Next one. B sub 1 is equal to 2, and b sub k plus 1 is 3b sub k. So this means the next one is 3 times previous. And so if it's 3 times the previous, then b sub 1 is 2, b sub 2 is 6, b sub 3 is 18. B sub 4 is equal to 3 times 18 would be 56, right? No, 54, sorry, 54. B sub 5 would be equal to 150 plus 12 would be 162. And then 162 times 3 would be 300 plus 180 plus 6. 46. Is that right? Let me check my math. Grab a calculator. 18 times 3 times 3 times 3. Look at that. Okay, so that's how we define this. So b sub 100, what's that going to be equal to? Well, if b sub 100, I'm going to multiply, so there's 99 terms. Let's see here. Really, every one of these, I take 2, and I'm multiplying it by 3. So this is 2 times 3 to the first, right? Well, then I'm multiplying by another power of 3. So this is 2 times 3 to the second, because 3 to the first, let me write it like this. This is 2 times 3 to the first times 3. So then the next one is 2 times 3 squared, because 3 to the first times 3 would be 9, times 3. So this would be 2 times 3 to the third times 3. And so my term number, so check it out. This is 2 times 3 to the 0, right? So b sub 100 is going to be 2 times 3 to the number of the term minus 1, because the second term has 1 power of 3. The third term has 2 powers of 3. The fourth term has 3 powers of 3. So this will be 2 times 3 to the 99th power, which is a huge, huge number. Okay, that's a huge number. So there we go. Limits of a sequence. For limits of a sequence is asking the question, does it go somewhere? And we've talked about this year, but it's been a while. And the general gist of this is pretty much like limits of functions, right? So it's a sub n is a sequence. Okay, a sub n is a sequence. And we're asking, does it go somewhere? Now, some of these don't go anywhere. So like if you look up here, check this out. So 5, 10, 15, 20, 25, 30, blah, 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 it goes to infinity. Well, that doesn't go anywhere. However, 1 over n, as it goes to infinity, as n gets infinitely larger, where's it going? Well, if you have a huge denominator, right, it's actually getting closer and closer to 0. And so this is going to be like Bobo, Betsy, Botu, in that we're going to evaluate the numerator and the denominator and what's actually happening here. So here's what it goes. If a sub n has a limit where the limit as n goes to infinity, so n is getting increasingly large, of the sequence a sub n is equal to L, then it converges. If not, it diverges. So we're asking the question, does it converge somewhere? Does it go somewhere? Is it going to 0? Is it going to 5? Where is it going? Or is it divergent, meaning it just keeps going on into infinity? So let's take a look. I've got to write in these examples as we do them. We're going to do 2. So let's take a look here. My first a sub n is equal to, so this is a sub n is equal to 1 over 1, 1 over 2. I spoiled the surprise on this one. 1 over 3, 1 over 4, comma, dot, 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 to 1 over n. Well, if you think about it like this, we're going to evaluate the limit as n approaches infinity. And this isn't unlike 1 over x, right? So that would be bigger on bottom, right? Because my exponent on the bottom is bigger. So Bobo means that my limit equals 0. Actually, there's an asymptote at 0, but the limit is 0. So the limit as n approaches infinity of 1 over n, and this is exactly how you'd write it, is 0. So that means it's convergent. It converges to 0. B. Here's my next one. 2 over 1, 3 over 2, 4 over 3, 5 over 4. What's happening here? Well, you have n plus 1 over n. And so I want to compare the highest powers, right? So essentially what's happening is I have the limit as n over n plus 1, as n goes to infinity, of n plus 1 over n is equal to, essentially, so you always take the highest power. So I'm really looking at these two. Compare highest power exponents. And when I compare the highest power exponents, it's equal to n over n, which is equal to 1. So my limit is 1. Why is that? Well, as it gets to a million. Well, 1,000,001 over 1,000,000, 1 is not that significant when you get to a million, right? So a dollar bill to a millionaire is important. I'm not saying it's not important, but it becomes less important. The more money you get, the less 1 cent, $1 becomes. Now, when we're down here, yeah, 2 over 1 is significant. That's 2. 3 over 2. Okay, so it's shrinking, but it's going toward 1 here. So this is convergent. C. 2, 4, 6, 8, 10. This one's going to be divergent, because this is 2 times n, right? So the limit as n approaches infinity of 2n is equal to infinity. It just keeps going, it keeps getting bigger. So what you're going to see is a lot of times it's a ratio, right? So we've got a fraction of some sort, a rational expression in there, for lack of a better term, that's going to give us where we actually have a limit. D. Negative 1. 1, negative 1, 1, negative 1, 1, dot, dot, dot. negative 1 to the n. The limit as n approaches infinity. Well, you can see what's happening here. It's negative 1 to the n, so odd powers are going to be negative 1. Even powers are going to be 1. Well, the limit does not exist. It doesn't exist because it just keeps going like this. Right? So up and down, up and down, up and down. It's not going anywhere. Okay. Let's keep rolling. Keep rolling, keep rolling, keep rolling. Talk about arithmetic sequences. Arithmetic sequences look like this. A plus D, A plus 2D, A plus 3D. Well, what does that actually mean? I'm going to keep going here. A plus n minus 1 times D. So it would look like this. 2, 5, 8, 11, 14, dot, dot, dot. 2 plus n minus 1 times 3. Okay, so you can see what's happening here. An arithmetic sequences adds the same thing to each consecutive term. Okay, so we're adding 5, adding 3. Well, what that gives us is D is our common difference. D is the common difference. So if D is the common difference, what happens is this. A sub n is equal to A sub n minus 1 plus D, so the term before plus D, for n is greater than or equal to 2. So it starts with the second term. The first term is whatever it is. It starts at 2 or 5 or 18 or negative 6. But then you're adding the same thing to each term. Okay? So here we go. Let's look at a couple of examples. So for each of the following arithmetic sequences, so this should be A sub n minus 1 plus D. Find the common difference. What is added? The 10th term and a recursive rule for the nth term and an explicit rule. So we're going to talk about explicit versus recursive here in just a minute. So take a look here. How do I get from negative 6 to 2? Add 4. From negative 2 to 2, plus 4. So my common difference is 4. That's what I'm adding. Okay? And so my 10th term is equal to negative 6 plus, now A sub n minus, so my formula here is A sub n minus 1 plus D, right? So I got to have the term beforehand. Well, how am I going to define this sequence? Well, what I can do is define it based on my common difference and the term before. So negative 6 plus A sub 9 times D, right? So I know my common difference of 4. This is going to, we need a little bit more information. So look up here. So up here, this should say A sub n. A sub n, what is going on here? A sub n is equal to the previous term plus D. Well, yeah, that's great, but this is a recursive rule. And it works if you're starting at the beginning. It's defined by the term before. What we want is an explicit rule. And an explicit rule allows you to pick up exactly at any term. So it's any term, and it's taking us from needing every single term previous to saying I can jump into the middle of the sequence to A sub 1500 or whatever. Explicit rule looks like this. It's the first term plus n minus 1 times D. Why does this work? Well, because you're adding the same thing every time. Let's look up at this example here that I gave you. Because I started at 2 and I added 3 every time, by the time I get to 8, I did 8 is equal to 2 plus 2 times d, my common difference, is equal to 2 plus 2 times 6, which is, no, 2 times 3 is my common difference, which is 8. Because you add the same thing every time, and you started somewhere, you say what I started with plus the number of my term minus 1 times the common difference. Jump down here. I started at -6, and I'm going to add a multiple of 4 for every time I step up to 10, except I need one less because I started at -6. So I'm going to do 10 minus 1, because that's my n minus 1, times 4. So I've got -6 plus 9 times 4, which is going to give me -6 plus 36 is equal to 30. That's my term right there. Okay? I need a general rule. Okay, so I need a general rule. So my general rule looks like this. Explicit rule. Looks like this. -6 plus n minus 1 times 4. I'm going to distribute this in. So I've got -6 plus 4n minus 4. So I have 4n minus 10 is my explicit rule. What did I just do there? Well, I expressed what I already knew. I expressed my explicit rule. I just distributed it out so I can always do this. So what's it going to mean? If I put in 10, I've got 40 minus 10, which would be 30. All right, number 2 is kind of tricky. What I'm going to do is I'm going to find my common difference. So d is equal to, and I'm going to subtract terms. So subtract terms that are consecutive. So I've got ln6 minus ln3. Or natural log 12 minus natural log 6. Or natural log 24 minus natural log 12. It doesn't seem like there's a common difference here. It seems like these things should have some like multiplication connection. But if you remember the rules of logarithms, check this out. ln6 minus ln3 is actually equal to the natural log of 6 over 3, which is the natural log of 2. The natural log of 12 minus 6 is the natural log of 12 over 6, which is the natural log of 2. The natural log of 24 minus natural log of 12 is the natural log of 24 over 12, which is actually the natural log of 2. So my common difference is actually the natural log of 2. If I use my formula here, a sub n is equal to the natural log of 2 plus n minus 1 times my common difference. This should be, sorry, this should be the natural log of 3. That's what we started with. So it's what I started with, a sub 1, plus the natural log of 2 times n minus 1. So a sub 10 is equal to the natural log of 3 plus 9 natural log of 2. Well, when I combine those things, which I can do, I'm going to end up with the natural log of, and these are going to be, so this is actually the natural log of 2 to the 9th power. Remember, because the exponent comes out front. So this is the natural log of, and then addition means multiply. So 3 times 2 to the 9th, which is equal to the natural log of 1536. That's my 10th term. Okay, and my general rule would be my natural log of 3 plus n minus 1 times the natural log of 2. That's a tricky one. Let's talk geometric sequences. Geometric sequences have a common consecutive ratio. So, for example, 2 and then 6 and then 18 and then 54, what we talked about last time, right? And so it's going to be this common ratio of multiplying by the same thing every time. What we came down to was this was really 2 times 3 to the 0, and then 2 times 3 to the first, and then 2 times 3 to the second, because I multiply by the same thing every time. right? And so I multiplied by the same thing every time, which increased the power on that 3. And so this really came down to 2 times 3 to the n minus 1. Okay? And my common ratio would be 3. So R is my common ratio. And it's found by doing 6 over 2 is equal to 18 over 6 is equal to 54 over 18, etc. You take the ratio of 2 consecutive terms, and that's going to give you your common ratio. Let's work on this. For each of the following, these are geometric, geometric, geometric sequences. Find the common ratio, the 10th term, a recursive rule. So that's starts with 3. 6 over 3 is equal to 12 over 6. And this is how we test. You know, sometimes they're going to say, hey, here's a sequence. Is it geometric or arithmetic? Well, are you adding something the same every time, or are you multiplying something the same every time? I don't know. In this case, they told us it was geometric, but we could always test it. So is 6 over 3 equal to 12 over 6? Equal to 24 over 12? Yes. So my common ratio is equal to 2 because my common ratio, so I got to multiply by 2 every time. So this is what it looks like. If I pop back up here to find a general rule, okay, so this is all well and good. That's up there. So for geometric sequences, a sub n is equal to a times r to the n minus 1. That's exactly what we found over here, right? And so you find what that common ratio is, and because you multiply by every single time, it's where you start, and then a power of that common ratio minus 1 because you didn't do it for the first one. So when I take my common ratio here, so I want to find the 10th term, right? A sub 10 is equal to 3 times, and my common ratio is 2, and I want to do that to the 9th power, right? So that's going to be 1536. That's my 10th power. So what is my recursive rule? My recursive rule would be a sub n is equal to the term before it times 3. That's recursive. Explicit, so this is recursive. And explicit is a sub n is equal to 3 times 2 to the n minus 1. Let's check out this next one. What does it look like? 10 to the third, 10 to the negative 1, 10 straight up. So 10, 1 over 1,000. This is what I was telling you at the top of this video was sometimes you got to rewrite it to make it look a certain way, and so you can kind of see what's going on. But if you're lost, kind of write this, right? So what's happening every time? That should be 10 and 10 to the first. Did I write this right? Hold, please. I wrote this wrong. I typed it all wrong, guys. I'm so sorry. This is what it actually should be. 10 to the negative third, 10 to the negative first, and then it should be 10 to the first. I'm like, this does not create a pattern. You guys are probably sitting out there going, what is he doing? Who is this guy? Is this on the internet? They allowed this? All right, so this up here, that was fake news. That was not real. So here we go. This one, however, is real because it steps down by 2 every time, or steps up by 2 every time, depending on how you look at the number of zeros, okay? And so what are we talking about here? A sub 10 is actually going to be equal to 10 to the negative third. That's my first term, so that's A sub 1. And then times, and I'm going to be multiplying this by each consecutive set, what the common ratio is. Well, what's my common ratio? I've got to make my common ratio. So 10 to the negative first over 10 to the negative third. What? Do an easier one, right? What if you did 10 to the third over 10 to the first? So that would be 1,000 over 10. So it would be equal to 100, which is 10 squared. Okay, and if you did the math, and if you did the subtraction here, it'd be -1 minus -3. So 10 to the -1 plus 3 is equal to 10 squared. Okay, those match up. So my common ratio is equal to 10 squared. So I take my first term, a sub 1, and multiply it times r, so 10 squared. And that's got to be to the n minus 1, so 10 squared to the 9th power. And so when I get this, it should be 10 to the -3rd times 10 to the 18th. And when I add those, I get 10 to the 15th power. Sorry that this is kind of confusing potentially. This was a side note down here. Right? So 10 to the 15th is my 10th power, and my recursively defined rule would be 10 to the common ratio, so 10 squared times a sub n minus 1. And my explicit would be this. It would be my 10 to the -3rd, so my first term, times, and that's going to be 10 squared to the n minus 1. Okay? All right, last problem here. I know this is kind of long, but this is a super, it's an involved lesson, but I think it's something that's pretty straightforward you can do. I've got this term, these terms, right? So the second and fifth. So here's what I like to do. 3, 4, 5. So my second term is 3. My fifth term is 24. Okay? So what that means is that 5 minus 2 is equal to 3. That's my change in n, right? My delta in n, my change in n. So it's changed 3 places. So if you want to think about it a different way, this is a sequence. Let's see if it's arithmetic, right? Got to figure out what it is. That would mean I take the first term and I'd add my common difference, and then I'd add my common difference, and then I'd add my common difference, and I'd add my common difference. So to get from 2 to 5, my second to my fifth term, it would be 3 common differences. Does that make sense? My total change here, my total change in a sub n is 24 minus 3, which is 21. So that means that my total common difference, my total change is 21. And my total change in n is 3. So 3d is equal to 21, because there's 21 total change. And my common difference, number of times I've used it, is 3. So my difference is 7. So to get from my second term to my first term, I've got to do what plus 7 is equal to 3? Well, so that would be -4. So a sub 1 is equal to -4. So that would mean that if I'm trying to find explicit formula, that would be -4 plus common difference times n minus 1. So my formula is equal to -4 plus 7n, I'm distributing this in, minus 7, which is equal to a -11 plus 7n. And so if I want a recursive formula, it's going to be a sub n is equal to a sub n minus 1 plus 7. All right? That's all there is to it, guys. That's the first part where we do it as an arithmetic sequence. Let's do it as a geometric sequence now.